Now we will talk about the second lab assignment, where we will cover memory models and how different memory orderings can have an impact on the consistency and correctness of your application. So let's start by taking a look at the files you need for this assignment. On the course forum, you'll find the handout, as we had for the previous lab, and you will also find a compressed tarball, which contains all the necessary files that we need to solve this lab. Each of these files is implementing a different thing that we will cover now, but let's start by taking a look at the handout first. So in this lab we will try to cover the basics and try to learn how important synchronization is, and especially how different memory ordering and memory models implemented by different architectures can have a huge impact on the correctness and consistency of the applications we are running on. And we will do that by taking a look at the very simple algorithm that we will implement. And the problem with this algorithm is that when we implement it and run it under different relaxed consistency models, memory models, we will see that it's not working at all. And we will take a look at three different ways of how to fix this algorithm, this implementation, and compare how well they performed and what are the pros and cons of using these three different synchronization mechanisms. So let's start by taking a look at this algorithm and try to understand what the application is doing. So this is an algorithm that it's supposed to run in multiple threads. So it's an application that is running multiple threads, and each of these threads are operating on some variable that it's going to be shared. So in this case, the shared variable is called shared data, as we could see here. And we will start by setting up this shared variable to 0. So what we know is that when each thread starts executing, the value of shared data will be 0. And then what we will do is we will iterate a certain number of times. In this case, this is defined by n. And we know that each thread that it's executing can be identified by a unique ID. So what we will do is basically check the ID of the thread, and we will do something different for each thread. So in this case, let's say we have just two threads, and what we'll do is if thread 0 is the one who is running, then thread 0 will take the value of this shared variable and will increment it by 1. The other thread 1, will do the same thing but decrementing the value of this shared data. So intuitively, if we try to think about this algorithm, what we expect from it is that by the end of the execution of this application, we should be able to see 0 in this shared variable, because we have one thread on one hand that is constantly incrementing by 1 the value of this shared data, no matter what the value is. And on the other hand, we have this other thread that is constantly decrementing the value of the shared data, and they are doing this the same number of times. So by the end of this application, thread 0 have basically incremented the shared variable by n, and thread 1 decremented by n, so we expect to have 0 as a result. However, we know that this is not the case in many architectures, because we know that the requests for loads and store can be reordered, and this reordering can cause to have read outdated values, and when we write back these values to memory, then we will be writing the wrong values because we were working on old data. So we know that this algorithm is very simple, and we know that it's not working in many implementations. So what we will do here is try to fix it. And if you go back to the files, let's take a look at the files we have here. first of all, you will see that we have two files that are called lab2, lab2.h and .c. And we have these two files because these two files are setting up all the environment we need to run and test different implementations of the same algorithm, that this algorithm one that you can see over here. This is very convenient because this is the framework we will use to try them out and to see if they are working or not. You don't need to modify these two files. Feel free to take a look at them. You'll see that here we define many structures that we need and all the basic code that is needed to get this running and try all the different implementations and all the different types of implementations that we will be using to fix the problem that we described in this code. That regarding these two files. And then you will see that we have this tests file down here. And the first thing you will need to do is, if you check the testcritical.c file, if you open it, you will see that here we have implemented already this algorithm. So we have some code in this function called increase, and this is the code that thread 0 will be executing. And on the other hand, we have decrease, the decrease function, that this is the code which thread 1 will be using. The rest of the code down here you don't need to pay attention to. It's just to prepare the framework we were talking about in the lab2.h and .c files. But if we focus on these increase and decrease functions, these are the codes for thread 0 and thread 1. And as you can see here, they are iterating the same number of iterations, and they are bringing the data. The data is the value that the shared variable has at a certain point in time. They are incrementing, in this case, thread 0 is incrementing the data and then it's storing the data back. And the dual thing with thread 1, it's reading the data from the variable, it's decrementing it, and it's storing it again. The problem we have here is that we know that this is not going to work because of how they interact with each other, and the fact that we are reading the data and then updating it could be interleaved with some other instructions from this other processor that it's reading the data as well and decrementing it. So when they are actually going to write the data back, the results are going to be outdated. So our first task is to fix this code, fix this testcritical.c file to make it work. We will start by doing this by inserting calls to enter critical and exit critical. So we will define critical sections where if we do that, we know that each thread that it's in a critical section, it's modifying a shared variable, and then all the other threads that want to modify the same variable, then they need to wait somehow until this thread released the variable. And by doing this, we will know that only one modification at a time is allowed, and all the threads will be reading and writing the proper values, because there won't be overlaps in the values that they are reading or writing. The problem with these critical sections is that if you think about it, we could use them in a very silly way. So let's say that we start thread 0 and we enter a critical section, and then we don't exit the critical section until we finished doing what we wanted to do. So in this case of this application, this would work. So let's say we put this enter critical at this point, and then we exit critical at this point. So this would work in this particular case just because what thread 0 is doing has nothing to do with all the other threads. So this thread 0 is progressing no matter what the other threads are doing. So we have this progress guarantee here, so we won't have problems like starvation or deadlocks because this thread is waiting on the values of the other threads. But despite the fact that this approach will work, we are doing this in a very dumb way, and we are causing all the other processors and all the other threads to wait. And this is a very greedy way of doing this. The point is that when we try to insert and determine critical sections, we want to minimize the amount of work that can be done or that is done inside the critical section, so that we can guarantee fairness among all the threads as well. So in this case, this solution is not fair because the first thread that is acquiring or entering the critical section, it's going to be there forever, and it's not giving the chance to any of the other threads to progress as well. So your job here is determine a good point here in this code to enter and exit the critical section, and you will need to do that in both cases, in the code for thread 0 and in the code for thread 1. And once you have done that, this should work. And the reason why this should work is because the first code you will use to try this out is the code that is already implemented in this file that it's called critical sections pthreads. When you insert these critical section calls to enter critical and exit critical in these two functions, these calls will execute a synchronization mechanism that is implemented in all these files here. And these are the ones that we will try out. We will implement these in different ways. And the first one you will use is the pthreads implementations. If you open the critical section pthreads file, you will see that the implementation for enter critical is basically just calling the synchronization primitives of the pthreads library. This is not very smart. It's good if you don't want to reinvent the wheel, because we are using a library that it's already done, it's already created. And but in this case, we want to reinvent the wheel. We want to create our own implementations of how to enter and how to exit a critical section, because we want to measure and learn about the differences between all of them. In this case, we have 3, but it could be more than that. And if you come out with any new idea of how to synchronize things properly, then this is the way to proceed. So if you try this implementation out, you will see that this works, but this is not what we want to try. But this is just for the sake of correctness. You will see that this is using an external library, and this can create a very, very huge overhead on the performance of the application. So that's the first part of the lab. If you go down, you will see first a description of the files, as we are doing here, but you will also see this tasks list. It's basically a to-do list, and you will first insert the critical sections, determine a good place to insert those critical sections, and try this out with a pthreads implementation. The second thing you will try out is implementing the Decker's algorithm. So here is an outline of the Decker's algorithm. You will see the listing here for algorithm 2 is the Decker's algorithm. And you will implement this algorithm in this file called critical section Decker. If you open it, you will have enter critical and exit critical, but now using the Decker's algorithm. We've inserted these hint lines as with the previous lab to give you some clues about what to do and where to do each of the tasks. Finally, you will have to implement these critical sections with atomic and non-atomic, using atomic increments and decrements, and using compare and exchange, also atomic instructions. So these two implementations you should do in this test compare exchange.c. If you open it, you will see the same thing, some code for increase, some code for decrease, and here in these two functions you will implement a loop that is increasing and decreasing the variable, but in a non-atomic way. It's a non-atomic compare and exchange. So you will see here what happens because you're doing multiple operations, the comparison and the exchange. And you will also do the atomic increase and decrease, that it's doing the same thing as with the other two functions, but with using atomic instructions instead. And we will compare the timing between both of them, and also the atomic and non-atomic increment and decrements. So here you will see increase and decrease, and you will just use increments and decrements assembly instructions to increment and decrement, but you will also use atomic assembly instructions to increment and decrement the same variable. Remember that you are always implementing the code in algorithm 1. The slightly more complicated part is when you need to implement the code inside algorithm 2, that it's basically the Decker's algorithm to enter and exit the critical section. But the rest, you should always keep in mind that you are working with this very simple example where you have two threads that want to increment and decrement a shared variable. So now let's talk a bit about how to execute these things, because we have said that you need to implement different ways to enter and exit the critical sections, but we never said how to try it. So if you open a terminal and you go to the folder where you have your files, the first thing you'll need to do is just type make with the previous lab. So now that we have our application compiled, we can try it out by just calling lab2, and if you run it, this will try a default implementation that is just trying the critical implementation, the critical section implementation using pthreads. So this is the default implementation, and it's doing this number of iterations. It says also how much time it took for each of the threads, and the average execution time between both of them, among all of them. But that's not the only implementation we want to try, so let's clean up a bit here. And if you run this application with -h, you will see a help message here, and this displays different options we can give to the application to try out different implementations. So for example, here is if we add this parameter -c and we give a name of any implementation, then the program will execute that implementation in particular with the same application, the implementation of the algorithm 1. And if you want to see further information about these different implementations, let's say we want to check all the available implementations we can choose from, we can just do -c and type help. This is basically saying, I want to run some implementation, but I don't know which implementation you support, so give me a help message of all these implementations, and you will see that you could select different implementations of these enter and exit critical sections. The one we will be trying out, and it's already implemented, is using the pthread library and using the pthread mutexes. You also have a null implementation. It's very good to try it out. Just give it a shot and take a look at, compare this implementation against the pthreads. Of course, this implementation is the one that has the problem where we could see consistency issues because we are not updating the right values. But it's good to take a look at the performance issues comparing both of them. You can also select the Decker's algorithm implementation for the critical section, and the CLH Q logs. This is the bonus part of this assignment that we will talk in a couple of seconds. So if you want to try this out with the Decker's algorithm, you can just type -c Decker, and this application will run with the Decker's algorithm implementation of the critical sections. You can also select, if you go back to the help, you can also select the number of iterations this program is running, these threads are running. And you also have this other parameter that it's called -t, that is -t test. And here you can select among all the different implementations we have for the same algorithm. So we have different implementations for the critical sections, but we also have different implementations for the same algorithm. And this is going one step further. So we are talking about the same problem here, that basically is running two threads at a time, operating on a shared variable. But if you take a look at -t help, you will see all the choices for different implementations that are the ones that you will be implementing on these files we just looked at. If you choose a critical option, this is the one that it's going to be used by default. This is protecting the data, protecting the shared variable among the threads using critical sections. And you can run the same critical implementation using 4 threads or 8 threads at the same time. So this is going to grab your implementation of the critical section that you implemented either in this QCLH logs or in this Decker's algorithm or the pthreads. But it's always going to use critical sections, entering and exiting critical sections. Now, if you choose the increment, decrement, non-atomics, you will use this other implementation of the algorithm that it's going to be in test increment decrement.c that we just looked at. And it's the same with the increment decrement atomic in the same file, and with the compare exchange implementations of algorithm 1. So this is the to-do list you have here in the tasks section in the handout. To recap, we will first go through determining where to insert the calls to the critical sections, and then go ahead and try that out with the pthreads reference that's already working. And once you check that this is working, you can now be sure at this point in the lab that you inserted the critical sections correctly. So before moving on to the rest of the lab, try this implementation out, the pthread critical section version, because now you should see consistent results among by the execution of both threads. Once you have inserted the enter and exit critical in the right places, you have identified the critical sections correctly, and then you can move on to the rest of the lab that is basically changing the implementations for the critical sections. If you move on to point 3, you will implement the Decker's algorithm for the critical sections. And finally, you will move to the last two points here, that it's implementing the same algorithm 1, but now it's not using the critical sections. It is using atomic and non-atomic assembly increments and decrements. Here's a comment that I should highlight, that it's that you should use, for these atomic and non-atomic increment and decrements, you should use the assembly instructions that you have provided here in the lab2 asm.h. So if you open this file, you will see that you can call asm atomic inc in 32 to a variable, and this will execute this atomic. These are basically just wrappers to this awful code that you have here, and these are the ones you should use. So in these 2 points, you should implement the algorithm 1 using atomic increment and decrement, and also atomic compare and exchange. Then you have a couple of questions to reason about the performance, since each time you run the application, you get some numbers on the time it took to run each of the threads and the average waiting time. We have some questions here to reason about the results you are seeing. And finally, you will find this bonus part that it's implementing a third type of critical section that is using CLH locks, and you can go and find the details of those locks on the lecture about synchronization and memory models. And once you have recap all those slides, you can come back here, and you have sitting here you have this CSQ.c file that you could open and change the implementation here. We have prepared the code in a slightly different way, and this is just to help you out. We already have prepared the acquired and release calls and the initialization, and then you have the enter critical and exit critical. So in this implementation, you have everything set up, but the acquire and release. So you should go ahead and take a look at this code, try to understand it, how it's structured, and once you have done that, you should be able to slightly modify this code to make it work using CLH locks, and then try out this implementation using -c CLH or -c queues. Alright, so that's it for this lab, and I hope you have plenty of fun synchronizing different threads.